Hello everyone, welcome to Scottish Summit. In my next session, I'm going to talk about how to build a highly scalable and available cloud-native IoT solution for a contact tracing application on Azure. We're going to use the past offerings on Azure to build this contact tracing application. Before we get started, I'd like to thank our sponsors. Without this sponsorship, we won't be able to hold such a good event with so many good sessions from presenters of different backgrounds and from all over the world. Big thank you to Scriptrunner, Global, Proximo 3, Redspile, Agilysys, and Hitachi Solutions. Now let's get started. My name is Patrick Zhao. I'm a senior software architect and consultant at SSW. My company SSW is a Microsoft Gold Partner consultancy company here in Australia. Our headquarters is in Sydney with 4 other offices across Australia, different states. And we do also have 2 offices overseas in China. We specialize in Microsoft technology, such as .NET, Azure, and CRM. We help SMEs all the way to big corporates throughout their digital journey. We build web application, mobile application, native desktop applications. We love Azure. I'm on Twitter. I like to tweet about interesting technology trends, good ideas, and the highlight moment of my little one, who's at his terrible 2 at present. If you want to be a little bit more formal, connect me on LinkedIn. In my spare time, like other developers, I like to contribute to some open source projects on GitHub, and I do also have my personal pet project. At last, I have a blog. If I have time, I like to blog about the projects that I've been doing recently, the lessons I learned in my professional career. I have over 6 years of experience in fintech industry after I graduated from the University of Melbourne with a master's degree in software engineering. During my career, I have successfully delivered a number of different data analytics, IoT, and machine learning solutions to a wide variety of clients in fintech domain. I'm enthusiastic in IoT, big data, machine learning, and cloud technology. And also, I'm interested in front-end technology, especially Angular. I do run a Angular Hack Day and user group here in Melbourne. If you do have interest in sharing to Australian technology lovers, please do reach out to me. Thank you. Now, as I highlighted in my presentation subject, we are going to talk about a contact tracing application that I helped to build for one of my clients. When we talk about contact tracing, apparently it's in response to the COVID-19 pandemic, which is unprecedented in human history. I'd like to take a moment to review or recap on what's happening with COVID-19. So here is a daily change chart I grabbed from Google a couple of weeks ago actually. As we can see from the chart, we are pretty good, as in the daily average cases are dropping. This is worldwide situation, even though the 7-day daily average is still quite high. So please do follow the guidelines from your local government and health organizations to stay indoor, isolated. If we narrow down to Australia, we can see that from the chart I grabbed from Google, we are pretty lucky in Australia. We had the first wave back last February, March, and then the second wave in July, August. Although here in Victoria, we had a lockdown that ran for about 10 months, which was really a bad memory of every Victorian. We had to order groceries from supermarket, weddings and all other events had been cancelled. People had to stay at home. But now, we're getting pretty good. As you can see from the charts, the curve has been flattened. We don't have that many new cases. We are lucky, maybe because we are an isolated island as a whole anyway. Now, when things got better, people started to think about economy. Employers started to consider to get the employees back to work. But there was challenges. One of the biggest challenges was how to still implement the government's guidelines for social distancing as well as contact tracing in the workspace. That is the same with event organizers. So no matter for the employees who need to go back to a workplace or the attendees to an event, or even for individual visiting restaurants, how to better keep social distancing as well as monitor individuals' contact tracing history became a hot topic and challenge. One of my clients came up with an initiative to build this IoT solution where they call it Smart Badge to help employees to bring employer back to workplace. And in the meantime, still keep a good standard of social distancing rules and keep a good track of social contact tracing history and records. And this application can be used in events and a lot of other places. So what is contact tracing? World Health Organization has its own definition, but if we look at the definition from Victorian government, it highlighted a keyword called location. It says contact tracing is a process of gathering information about people who had coronavirus had contact with and the locations the person has been when they are infectious. In this sentence, the keyword is apparently location. So we need to be able to know the individual trace of contact or the trace of their locations they have been to. And we will know the position of the person in the room or in a big space. That's even better. Or we can remind or alert people when they became closer. That would be very good. If we put the initiatives to some bullet points, we can see apparently the contact tracing would be needed for events and workplace. From the commercial perspective, of course, we want the device to be of low cost, so that we need a dumb device. But the dumb device should be able to send data to the cloud for us to analyze, so that we will know the contact tracing history of the people who have been on the site. And as most other IoT solutions, it needs to be able to scale, and it needs to be available. You need to have the elasticity. At last, we want non-tech people to be able to understand the data and understand the insight came out from the data. We need to visualize it using some real-time charts and preferably heat map, so that it gives people a vivid understanding of what the situation is look like in an event space or workplace. From the initiative, we can figure out some key features of the product. First of all, it's a portable device, which is the terminal, or which is the end device that is used to gather the data. We call it smart badge. It could be a wristband, could be a lanyard, could be a card, could be anything, any gadget that's small enough to carry. But the features you need to have, or the functionalities you need to have, is be able to send data every single second of a location of that person, or we should say the position of the person in an event space, and also how far away two people are apart in that space. So you need to be at meters, if not millimeters scope. So the device can't be using satellites or big towers to send the signals. There has to be some on-site gateway to capture the data for that site. And now, of course, we want to stream the data, ingest it into some data analytics services on cloud. And that data analytics services need to be able to scale when there are a lot of people in the offices, the peak hours. And we want to run reports on it, want to run queries, we want to present it as a nice looking chart, pie charts, line charts, and those heat maps. And when two persons are getting closer to each other, we want to hit a beep from the device, that alerting the individuals, hey, don't get too close to each other. You need to keep social distancing. So based on the initiative, my client had come up with a prototype, or we'd rather call it an POC, that the development team developed. And it worked, but it had problems. Here is the architecture of the existing product. It looks okay, that it starts from a beacon, which is the gadget device that is dumb, but can send signals every single second to be captured by the gateway. And then gateway, acting as the aggregator, sends the information it received within the detection range of the gateway's radar, and send them in batch to a cloud MQTT broker. And then there's a Azure Function that subscribes to the cloud MQTT service and runs some analytic function. Next, it pushed off the reports or the query data to a web API, which would, via GraphQL subscription, broadcast to an Angular web app through WebSocket, so that the end user can see a live report in a visualized way. The architecture looks okay until we need to solve the problem for scalability. The Azure Function is okay, but when we need to scale it to be able to receive millions of messages, it is very hard to scale. It can scale vertically, but to maintain the state within each individual Azure function, it is very hard. Although we can use durable function and leverage some caching mechanism. And there's a special requirement for this solution. In reality, on a site of a space, it is very difficult and very, very expensive for a customer to buy a whole lot of gateways that be able to have a lot of overlap that cover the entire area. So what it means is that there's always some situation where a smart device, or sorry, a dumb device, they call it smart badge, disappear from a gateway detection, but not yet being picked up by another gateway nearby. So this is sort of the limbo state of a beacon. The business rule for this scenario is that they want to regard, or they want to see the beacon as being remained on the gateway area that it last appeared within the last 4 hours until it appears on another gateway. What this means in the Stream Analytics functionality is that the function we use to do the calculation need to be able to look back 4 hours sliding window. And that temporal window is very big. Every single second there's a payload. Even though the payload can be small, it's just a record of the location or the position of the person within the space. But if we multiply by the number of devices, the number of gateways, it becomes exponential. So each individual Azure function need to use a lot of resource to be able to run the analytics. And this can be a hybrid of memory and disk space. We can, of course, leverage a different caching mechanism or technology. But again, Azure Function is not designed for this purpose, or it's not the best tool that we can use of Azure for this purpose. So, as a recap or summary, the key technologies they use now is there's a message queue broker, and they use Cloud MQTT. And for the Stream Analytics part, they use Azure Function, and they've considered Orleans. Orleans is a nice NuGet library done by Microsoft Research, and it's on GitHub. It has a good amount of stats on GitHub. However, like using any .NET NuGet packages, there's always a learning curve, and you have to be able to program and understand the root of these two, instead of leveraging some existing cloud services. And at last, the real-time metrics is done via GraphQL subscription, which is good, but maybe there are other alternatives. Our client came to us with a list of requirements and the key features, and then talking with their development team, and we start to analyze the requirements from end to end. The requirement analysis starts with the dump device and smart gateway. The business needs the devices to be as dumb as possible using some protocol like BLE beacon or like an active radio frequency identifier, so that it does very simple and dumb things like sending a signal to a nearby gateway. As long as that signal has a payload of information for that beacon's location and how close they are to a gateway and how close they are to a nearby beacon, that should be good enough. Here I'm using beacon, badges, smart badge interchangeably in my presentation because that's what I call it. Okay? And then the gateway needs to be a little bit more smarter. Even though they call it smart badge, the real smart thing is the gateway. Although, for the time being, we might not need to run any analytics on edge. The gateway merely perform as an aggregator that is put the data together, send them as a batch, subscribe to a Cloud MQTT broker, publish to it. Then we come to the client-server popsup service. Here, when we talk about the client-server popsup, there are two main categories. The MQTT, short for Messaging Queue in Telemetry Transport, which is optimized for centralized data collection and analysis, as opposed to DDS, Data Distribution Service. And the name tells what it does. It's optimized for distributed processing, directly connecting sensors, devices, and applications to each other without a centralized IT infrastructure. And in our case, since we the end goal is to generate some centralized visualized report and heat map, apparently we need to use MQTT rather than DDS. And they choose to use Cloud MQTT service as the MQTT broker. There's nothing wrong with it for the time being. Now, if we take a look at Azure PaaS offerings for data ingestion services, we'll find that there are a couple of different options out there. There is Azure Event Hubs, which is a multi-purpose event data ingestion service that can be used for a variety of different purposes. If you look specifically for IoT solution, there is Azure IoT Hubs, which is designed to support enterprise IoT solutions. And Azure also supports Kafka on HT Insight. Here, there's a table of comparison for different type of data ingestion processes, different type of event sourcing hubs from Microsoft Document Repository. As we can see, IoT Hub is the sort of out-of-the-box solution. It supports MQTT, supports AMQP, and even HTTPS, which looks awesome for the case. But when we consider about our client's existing architecture, they've already used Cloud MQTT as their message broker. We probably don't want to refactor that part at the initial phase. They've already invested in a Cloud MQTT subscription, and the popsup service works okay. Plus, if we want to use IoT Hub, your device, and in my story, the device is the gateway, need to be programmed to be able to talk to IoT Hub, which is not hard. There's plenty of ways to do it. Azure IoT Hub offers SDK in different languages. Again, that's embed software development need to happen at some stage. So we probably would want to use Event Hub in this case. We still have a dedicated web app or Azure Function serve as a ingestion subscriber that listens to the Cloud MQTT broker. Whenever there's any event passed through from gateway, it ingests to our Event Hubs from that dedicated web app or Azure Function. And that web app or Azure Function is very easy to scale because the tasks it's doing, it's quite simple. It's merely just pass through the data to the subsequent Event Hub and then for the analytics engine to get the data. Good. Now we have the data ingested from our event sourcing services. Now we can start thinking about how we process the data we've got from the event sourcing tools. The existing solution uses Azure Function. There is nothing wrong with using Azure Function, but as I said before, in order to scale up Azure Function, we have to host it as an app service, as a premium plan. But then it comes to the same problem of scaling up an Azure app service, which is difficult and hard to manage and automate. Secondly, Azure PaaS service has an offering on Azure App Service, which is Azure App Service Web Jobs. So we are probably all familiar with Handfire, which is .NET library on NuGet. And web jobs somewhat work similar as a Handfire job. With an app service, you can host recurring jobs that can use the same resource that you dedicate to the app service to run some analytics. But for this IoT solution for big data, web job come to the same problem as we had with Azure Function hosted on an app service plan. To scale up, you need more RAM for an app service. It's hard to manage, hard to automate. Azure also supports Kafka Streams API. Kafka as an Apache open source platform, it is good for streaming and also analytics, but it's not first-class citizen. And plus, we don't have the knowledge on Kafka, so we decided not to use Kafka for this project. Next is the Azure recommended tool for a lot of event sourcing and IoT solution, Azure Stream Analytics. We ended up using Azure Stream Analytics. I tell you upfront, But there are a lot of considerations on this, which I'll come to more details in next few slides. Azure Stream Analytics use a SQL-like language, so most developers know how to write it. It's declarative, and it can automatically scale up and scale out by using Azure automation. And the way it works is somewhat close to Azure ML service or Azure Databricks, that you can have a concept called a cluster, and with Azure Stream Analytics, it's called streaming unit. You can dynamically allocate more streaming units to it. It is behind the scenes, no doubt, some type of VM, but it hides that infrastructure from the users. The users can focus on leveraging the concept of a stream unit for the scaling. And also, it has terminologies and modules that's specifically designed for stream data processing, such as watermark delay, partition, and in-job partition. And at last, as a comparison to Azure Stream Analytics, there's a more, I would describe it as a more fully featured engine, Spark. So Spark is another Apache open source project. Azure's offerings for Spark sits with HD Insight as well as Azure Databricks. Databricks is the company looking after Spark, originated from open source project and then joined the Apache family. And Azure happened to be the biggest investor behind Databricks. So Databricks is one of the first class citizen on Azure, and Azure has a very good support for Spark. The main consideration for not using it may be that the learning curve is steep. Now, if we look at the capability matrix, we'll see that Azure Stream Analytics is a declarative sort of programming model. You use the SQL-like query language, whereas HD Insight, you can have a mixture of different languages. You can use C#, F#, Java, or Scala, because it's Spark. So Apache's Spark in Databricks is somewhat similar because they're both Spark. And there's another option called HD Insight with Storm. I haven't used it before, so I can't comment on that. Azure Function, everyone knows, it's procedure-based, it supports a wide range of languages. Now, the pricing model for Azure Function does not specify the option for app service plan. But apparently we can host it on app service plan, but then it comes to the problem that it's hard to scale up and scale out at the same time. Web Jobs is attached to Azure App Service, so the programming model, the pricing are all the same as an Azure App Service. Now, programming model for the first three options, Azure Stream Analytics, and the two options for Azure Spark on Azure, either HD Insight or Spark and Databricks, they're both charged by some sort of cluster or unit. So the cluster or unit are all abstraction of some underlying infrastructure. So this way you don't need to worry about the actual infrastructure, whether they are shared on the same rack or they are dedicated or anything. All you need to know is that within a certain unit, how many jobs or how much computation you can run within that given environment. So from this perspective, it's easier for you to keep track of how much you are spending versus how much computation power you are getting. So once we've done the streaming and analytics, we can think about how we're going to run query and get some reports out from it. So when we build a web app to show the charts and do the reports, of course, the traditional way, the old school way of doing it is the request response model via HTTP, either via a short polling or long polling. So the polling means that the client web application would send request, would ping the server every certain period amount of time, every 1 second, every 3 seconds, and get a response back. So you will update the rendering of the data as a chart, as a map, as a whatever, presented on front end every certain period of time. And in comparison to that, there is a server-sent event, which is driven by the server. So server pushes information from the data source, which is sits on the server. It could be a web app, could be an Azure Function, could be whatever server-side programming model, pushes down to client browser to render it. It looks great if the client does not need to communicate with the server to specifically ask for a certain type of data. If it's completely server-driven, then the server-sent events are okay. But we need to bear in mind that not all the browsers support the server-sent event. As far as I know, some old browsers, old IE7, IE8, definitely does not support it. So we need to make sure that the server-sent event is supported on the browser that our application runs on. And then the last is WebSocket, which is the most common way of doing real-time report and heat map and real-time communication on the web. Like the chatbot application or a shared documentation application, they somewhat all leverages WebSocket. And on Azure, the offering for a WebSocket is SignalR. We used to use a NuGet SignalR, and Azure now has a PaaS offering SignalR service that helps developers to move away from hosting a SignalR Hub as a web app class. So a SignalR Hub class doesn't need to be on a traditional web app anymore. It can be a serverless hub on an Azure Function, which leverages SignalR service to do the scaling. So you only need to worry about the logic, but you don't need to worry about the scaling anymore. And then if you want to use GraphQL, there's an Apollo GraphQL subscription, which also establish WebSocket connection and do the real-time report and heat map from the WebSocket connection. Now, we've almost got a nice solution from the device on the edge all the way up to the Stream Analytics engine, and then to serve it as a real-time chart to display it on the browser end. However, there's a gap there. That is data storage. The Stream Analytics engine, no matter we use Azure Stream Analytics or Spark or whatever, the end result would be some type of data. That's an aggregation or window function result of the stream data. That data need to be saved on some data store so that it can be easily fetched by the WebSocket server, either a SignalR or GraphQL subscription or whatever, so that the data can be served to the end browser. This way, we segregate the concern of the stream analytics part and the real-time charting server without interfering each other. Of course, we can bypass these parts by serving the data directly, but that way we lost a median layer, so that whenever anything happens and we need to troubleshoot, we don't know where to start because we lost the data store. Now, if we look at the big data offerings on Azure, there are different options. First of all, is file storage. And you might be surprised. Oh, can I save IoT data on a file storage? Of course you can. No matter it's Arvo data or JSON or any type of data, you can always dump it to a file and then save it as a CSV file or whatever text file on Azure Storage Account, Blob Storage, or Azure Data Lake Store, so that we can either have a copy of the data for backup purpose, or we can have it, leave it for later. There's also Azure NoSQL offerings. Azure Cosmos DB is a common option here for a document DB for a non-relational database. There is also H based on HD Insight. I'm not quite familiar with it, so I'll explore it later. And for our project, we need to consider caching because we need to render the heat map. And in order to render the heat map, basically there's timer saying every single second which pinpoint on the map should flash and which pinpoint should stay idle. And that data is better to be cached rather than stored in database and pin it every single second. So we might consider some caching technologies like Redis. Now, here's the refined architecture. Boom, it's completely different. Or it looks very, very different from the original existing architecture. I'm gonna explain this in details from beginning, from the device end all the way to the report end. I'm gonna turn off the camera so that you can see the full picture, and I'll zoom in. Now we've zoomed in. As we can see, the story starts from the end device, the beacons. The business case requires to support amount of beacons starting from 100,000 to 1 million. And these devices would send messages to a number of gateways, ranges from 1,000 to 10,000. And the gateways would aggregate the messages sent from the beacon, and that batch would be sent every single second to the cloud MQTT broker. As compared to the original architecture, we've replaced the listener of the cloud MQTT messages to a simple web app. That simple web app would merely pass through the information to an event hub that we call it raw input hub. This raw input hub would save a copy of the raw messages to a blob storage for archiving purpose. And then, as we can see, the raw input hub would dump messages to a number of transformers. Role of these transformer Azure functions is to take care of the incoming message and transform them to a unified format of data that can be recognized and processed by the downstream stream analytics. The reason why we need all these transfer functions is because the business orders the gateway from different manufacturers, and the different manufacturer has a different standard how they implement the gateway and how the gateway handles the messages. And the transform function feeds the data into an event hub so that the stream analytics can read the data of the event hub for further processing. Now, once the data is in the input hub, it breaks to two stream analytics. The reason why we use two different stream analytics is because we have another piece of requirements to be able to get the contact tracing details from the beacon up to the cloud and merge them to the real-time stream to run some further analysis. We'll talk about that in a bit. Let's first consider the real-time part. So on the real-time stream analytics, we will run that big window function together with some other temporal functions to know how many devices and which devices appear on this gateway, which devices disappear from this gateway. And those chart history is being written every single minute. So we have a look back of 60-second temporal window. And then the window aggregation result is written every minute to a Cosmos DB. We call it history container. So that via a web API, the contact tracing report can be generated and pushed to the front-end Angular web via the GraphQL subscription. And the Angular app is served via CDM. On another stream, the analytics job also referenced a traditional SQL Server for additional reference data, and together it forms a real-time occupancy which is essentially the real-time count of the devices on the gateway. And this would later be used to draw the heat map. And on the third stream, the analytics job would output to a service bus. And the service bus would later on trigger an Azure durable function, which serves as an orchestrator to send commands to devices. This orchestrator will also push information to a setup event hub. And this event hub feeds information into the setup stream analytics job, which accept the contact tracing report from the gateway. Setup hub also writes data to the web app so that the front end can know the real-time contact tracing report from each individual device. But that contact tracing report only remain for a day or so. And in order to display the real-time occupancy properly, with a high scalability, we introduced this GraphQL subscription cache, and we use Redis so that different instances of web apps would share the same caches to know the real occupancy on each gateway, like how many devices are on that gateway, that they won't interfere with each other. So now, as a whole, this chart shows us the overall architecture that we refined compared to the original architecture. So basically, what we did was we've broken the solution to different modules, and we use Azure Cloud native PaaS offerings for each individual part. Our high-level goal is to achieve a maximum end-to-end latency less than 2 seconds. Since we cannot fully measure the time consumption from the beacons to Cloud MQTT, we tried to measure the latency between when the device bridge gets the information to when user can see the charts change on the browser. Luckily, thanks to Azure Stream Analytics, it offers a watermark delay that can help us to somewhat measure this latency. In terms of the details of the watermark delay and how to use them, is not covered in this talk. I'm going to have a series of blog posts about Azure Stream Analytics and potentially Azure Databricks, and I'll explain them in details in those blog posts. Now, we've seen the full picture of the refined architecture. Is there any room for improvement? Of course, there's always a better architecture compared to the existing architecture. Now, with our refined architecture, we can see there's some overhead or additional steps with the Cloud MQTT broker. One of the biggest reasons is that it's not on a fully cloud native offering from Azure. So we can replace that part with IoT Hub. IoT Hub is able to handle different types of gateways, different types of formatted data ingestion, and then we can offload that transform function into different stream analytics jobs with the inner partitioning and a custom deserializer. When we did the project, the dedicated cluster for Azure Stream Analytics was not ready. So we got in contact with Microsoft and sort of work out what we could do and push them to make dedicated cluster available as soon as they can. And same as the C# custom deserializer. With those functionalities, we are able to save 3 or 4 different hops from the Cloud MQTT to the input hub. So the IoT hub is an input hub, and the custom transform functions are in analytics jobs. And as I mentioned before, another alternative for the real-time chart is signal service. And we can potentially replace the web app with Azure Function with different bindings and triggers to different other parts of the system. So this way this is cleaner. And later down the track, if we want to replace and fine-tune each individual module, we can certainly do that because they are all pluggable. For instance, if for some reason for the Stream Analytics engine, if we find out that Stream Analytics does not do its job, we want to replace it, we can try data breaks, and that's easy. We just need to replace this individual part. Here comes to the end of my presentation. As a quick recap, in my today's presentation, I've introduced you a real story of an IoT application that we built for our clients. I've showed you how we analyzed the requirement and architected for this contact tracing application from a dumb device, a IoT cloud message popsup service, and a stream analytics engine, then a real-time reports system, so that user can have an end-to-end experience from monitoring contact tracing details for real time. I hope you love this talk, and if you have any questions, feel free to ask me. Thank you very much.